Let's start. Okay, so happy Pi Day, everyone. Also, to celebrate Pi Day, we are very excited to have Francis Su, who will give us a talk about Sperner's lemma, a recent generalization with surprising applications. Thank you.
Great, thank you. It's great to be here. I'm really looking forward to this opportunity to get to know many of you over the course of this semester. I'm here through July, being hosted by Jonathan Sperner. My interest is in triangulations and some applications, which I'll tell you about today. This is where I teach. I just thought I'd say wave hello to sunny California near Los Angeles. It's a small school. It's called Harvey College. And one of the things I'm doing here, besides doing research, is organizing this seminar with Tillis, which I invite you to join us. The next one is on Monday. We're talking about the cultures of research in maths and talking about some papers by Tao and Mirzakhani and Gowers and Thurston, all on this topic. So invite you to join us on Monday. All right, let's begin. Oh, happy Pi Day, everyone. Happy Pi Day. We're going to actually talk about cutting something, not pies, but cakes later. Let me start with this game. This is a game called Hex. It was a game with hexagonal cells studied by Hine and Nash in the 1940s. Actually, Parker Brothers built a version of this game that you're looking at. And the idea of the game is you have 4 sides to this diamond. There's 2 X sides and 2 O sides, right? And the goal is you either play X or O. There are 2 players. And the goal is to basically create a chain of X's from one side, X side, to the other X side, or a chain of O's from one O side to the other O side. How many people have heard of this game? Okay, about half of you. Here's a question for you. If you don't know the answer to this question, you can vote, okay? Can this game end in a draw? Is it possible that you could end up filling up the board without creating a chain from the X side, between the X sides or between the O sides? Don't expect you to know the answer to this, but just imagine a board that's not 5 by 5, but 1,000,000 by 1,000,000. Can the game end in a draw? Okay, show of hands. How many people think you can end in a draw? How many people think you cannot end in a draw? Okay, so yeah, very interesting. We'll try to, you can puzzle over that if you get bored with anything else on this topic. All right, here's the plan. I want to tell you about something known as Sperner's lemma and talk about some proofs and an application that's dear to my heart. Then I want to tell you about a generalization that works for polytopes. And then I want to tell you about 4 surprising applications of this theorem. So here's Sperner's lemma. It concerns a labeled triangulation of a triangle. So here is a triangle that's cut up into lots of little triangles. And you notice that there are labels on the sides that are basically either 1, 2, or 3. And these follow this pattern that the corner simplices, the corner vertices are labeled by different labels, 1, 2, 3. And then all along the 1, 3 edge, you only allow numbers 1 or 3. Are you with me? Okay. And so similarly for the other 2 sides, 1 or 2, 2 or 3. And then on the inside, you allow any of those, 1, 2, or 3. Okay, very innocuous little combinatorial lemma from 1928. And so if you have such a labeling, something amazing happens. All right, and I want to first convince you that something amazing happens, then I want to tell you why we care. So here's something that's amazing, that there's going to be one little baby triangle, a triangle of the triangulation, that's a 1, 2, 3 triangle. Do you see one? In fact, discuss with your neighbor how many you see. Yeah, it looks like there are 3. And in fact, the number is always odd. And in particular, odd is never 0. Okay, so there has to be at least 1. This is a stronger version of Sperner's lemma. And it's an amazing little lemma. And it's true in all dimensions that by appropriate generalization. So if you go up to a simplex, an n simplex, there will be n+1 vertices, all labeled differently. And then if you're on the face that's spanned by certain vertices, then that vertex gets a label from one of the things in the corners. Are you with me? Okay. Very nice little theorem. This is what it looks like in 3 dimensions with 4 labels. And also something to note is that if you just take a face of this thing, like the 1, 2, 3 face, that's itself a Sperner labeling in 1 dimension. So many of the inductive proofs use that fact. Okay, why do we care about it? Well, it turns out that this little lemma is equivalent to the Brouwer fixed point theorem in topology, which is arguably a very, very important theorem, which says that if you take a map of a ball to itself, it has at least 1 fixed point. I'm guessing many in this room are familiar with sloshing a glass of water. And if you take a picture before and take a picture after, then there's a point in the water that must remain fixed, that must be in the same position in both pictures. Might have moved around in the middle, but we're just taking 2 snapshots. There's a point that's in the same place. And you know, the amazing thing is if you move that point out of its original position, you can't help but move another point in the fluid back into its original position. Okay, so there's something very surprising, very a topological fact here that there's always at least 1 fixed point. Another way I like to describe it is if you have a tank of fish and you slap the side of the tank with suddenly jarring all the fish, they dart in different directions. And the claim is if they dart continuously, which means nearby fish dart in nearby directions, then there's going to be at least 1 fish that doesn't know where to go and it just freezes. Are you with me? It's another way of thinking about it. Okay. Now, the thing about Sperner's lemma is that the Brouwer fixed point theorem was proved in 1910. Sperner's lemma came around in 1928. And in 1929, people started realizing this could be used to prove Sperner's lemma, which the usual way you learn about it, at least the way I learned about it, was in a graduate course in algebraic topology. Okay? And of course, you'll see many topological ideas come up in the combinatorics here, but it's arguably the simplest route to proving Sperner's lemma. And of course, why do we care about this connection between Brouwer and Sperner? Well, because Brouwer has so many applications, it's ridiculous, right? So in game theory, there's this thing known as the Nash equilibrium theorem, which if you watch The Beautiful Mind, it is explained wrong in that movie. That's a fun exercise to figure out why. But the idea here is that every game, so a game is an interaction between agents, between players, and every game must have an equilibrium that is a set of, so every player plays a strategy, and an equilibrium is a pair, or if you have n people, it's a set of n strategies, 1 from each player, that are mutually best replies to the other plays. Are you with me? That's an equilibrium. And I'm just going to try in a minute to give you a sense of how the Brouwer fixed point theorem is used to prove this, for which Nash won a Nobel Prize in economics. I mean, there's much that Nash did, but arguably it was for the Nash equilibrium that it is such a fundamental concept in economics. And so okay, so I'll just see if I can do this. 2 minutes, give me 2 minutes instead of a minute. Just going to give you a sense of how it goes. So if you imagine a normal game where you just have 3 strategies for rows and 2 strategies for column, get it, rows, column. You get to pick, rows picks a row and column picks a column. Are you with me? Okay. And if you look at this picture, you see that if rows picks B, column, who gets the green outputs, best reply is alpha. Yes? Now, that's unfortunate because if rows picks B and column picks alpha, the best reply to alpha isn't B. It's actually for rows, it's C. So this pair of strategies is not in equilibrium. And in fact, I've circled all the best responses for each of the strategies. Doesn't look like there's any equilibrium here. Yes? And so what Nash said is if you allow mixed strategies, if you allow randomization, then there must be a set of best replies. If you think of a game like rock, paper, scissors, that's a game that has a mixed strategy Nash equilibrium. The randomization 1/3, 1/3, 1/3 is the best, rock, paper, scissors. And so this is the surprise. There's a mixed strategy equilibrium. And the idea here is very simple. I was going to say Russell Crowe, but I mean Nash. Nash basically said, look at the set of strategies as a simplex, as a polytope, which is a product of simplices. Each person has a simplex of options if you allow mixed strategies. This is a product. And then here's the fish tank analogy. So at every point in this simplex, that's a pair of strategies that players could choose. Take an arrow and point in the direction of the better responses, if there are better responses to each person's pair, each strategy person's pair. And so that produces a vector field, if you like. I'm simplifying it a lot, but it's like fish darting. And so because of the Brouwer fixed point theorem, there's actually a point that doesn't move, and that's the Nash equilibrium. Done. Beautiful idea. In fact, I sometimes give this to my analysis class because it's a 3-page paper, and it's something you can do after they learn a little bit about continuity in analysis. All right, awesome. So here's another interesting connection to the Brouwer fixed point theorem. There's a theorem that actually says a game of hex cannot end in a draw. And Gale in 1979 proved that this is actually equivalent to the Brouwer fixed point theorem. So you can actually use the hex theorem to prove the Brouwer fixed point theorem and vice versa. That's an exercise that you might enjoy doing if you get bored with the rest of this talk. All right, okay, so yes. Two-dimensional hex, yeah. You could imagine a three-dimensional hex. It's not true if you had a three-dimensional hex with 6 opposite sides that you can do this. Yeah, there's no generalization that I know of. A good question. Probably just the two-dimensional. Yeah, that's a good question. All right, so let me tell you some proofs of Sperner's lemma, and these are the proofs you'll actually understand in this talk, because the others, once you see these proofs, you'll get the picture, which is mainly what we hope to get out of a talk, is the basic idea. So the first proof is actually Sperner's proof. It's a parity argument, and the idea is to go through this triangle. And every time you see a 1-2 edge, you place a rock next to it on both sides of this edge. So a 1-2 edge, we're going to call them doors. We're going to think of the triangles as rooms. And so every time you see a 1-2 door, you place rocks on either side unless you're on the boundary. Okay, so I've placed a bunch of rocks down. How many rocks are there? Well, I don't know. But if I just ask you if it's even or odd, I think you can tell that this must be odd. Why? Because they're pairs next to every internal door, and it's only the boundary door that matters. If you start at 1 and end at 2, then you have to flip an odd number of times. Okay, we're all good with that? Awesome. There's the induction. If you like, you want to think about this inductively. Oh, great. But now, like any good combinatorial proof, you count this sum a different way, where instead of counting by doors, let's count by rooms. You'll notice, if you think about it, that every triangle can only have 0, 1, or 2 rocks in it. Can't have 3. Can't have all 3 doors being a 1-2. You have to think about that. And in higher dimensions, the same thing is true. You want to generalize this. You can't have more than 2 rocks in a room. But the only time you get 1 rock is with a 1-2-3 triangle. Oh, nice. So there have to be an odd number, in fact, from this parity argument. Everybody happy with that? It's a nice proof. And you know, anything, often nice things in maths have lots of proofs. So let me give you a second proof. This proof is not constructive. It's a parity argument. And you might think, gosh, if I'm going to start using this to compute fixed points or compute Nash equilibria, then maybe I want a version that actually allows me to find such triangles efficiently. So here's the second argument, which emerged in the 1960s, and it became very popular in the operations research community as a basis of lots of algorithms for finding fixed points and Nash equilibria in nonlinear systems. So so what do you do? Oh, well, every door is a 1-2 edge. A 1-2-3 triangle is a room. Now, I just imagine walking from the boundary doors into the house. And if I see another 1-2 door, I just walk through it. If I see another one, I walk through it. And so what you either get are paths from the boundary that match up with each other, and a path that ends in a 1-2-3 triangle. And if there are any other 1-2-3 triangles, they should be matched up by paths as well. Very simple idea. Oh, and so why must they be 1-2-3 triangles? Because there's an odd number of boundary doors and only an even number of them get matched up. Yes? If you like that, you should let out a collective. Wow, that's so beautiful. It's beautiful. It's awesome. Okay. Okay, now I could tell you like 10 different proofs of Sperner's lemma, but I just want to point out that this one is the basis of a lot of, and its relatives, that there are ways to make this more efficient than this. So this means I don't have to search every simplex. I mean, because you could search them all exhaustively. So what do you mean by constructive? We just mean one that actually finds it relatively efficiently. But I'm going to show you one more because, I mean, this is a recent one. I've been thinking about Sperner's lemma for 20 years, and here's one that came out in 2007. I'm like, what? And it actually has some new ideas in here, okay? So if you really like this one, you have to like let out a collective, ooh, wow, okay. My favorite proof. So think of a labeled triangulation, take a Sperner labeling. And now what I'm going to do is I'm going to slowly deform the triangulation over time, where I take everything labeled 1 and I move it towards the 1 corner, everything labeled 2 and I move it towards the 2 corner, and everything labeled 3 moving towards the 3 corner. You with me? So I'm going to gradually deform it, and at some point it'll stop being a triangulation. But here's my cool keynote animation that I spent way too much time trying to make work. So do you see what's happening? I'm slowly moving all the purple things to the purple corner, all the green things to the green corner, etc. Yes? Okay. So it's using something called magic move in Keynote, which tries to match up things it thinks are the same. So it's a problem that may not always do that. Okay, so so here's the thing you want to notice. When I deform this like this in a little, for small time, this thing remains a triangulation. It's not going to have any overlapping simplices. Okay, it's also going to triangulate the whole simplex because you only have 1s and 2s along one edge. It's never going to like pop off. Are you with me? Okay, you promise you have to ooh and ah when you see this. Okay, so here's another, here's what happens if you go a little farther. Now those things are they're going to overlap at some point, yes? And it's going to look bad. So this is no longer a triangulation, is it? You with me? But here's what I want you to notice. If I take the total volume of all the simplices, that volume, if I move these vertices linearly in time, that volume is just a sum of determinants of all these things. So it's a polynomial function of time. Are you with me? Okay, so this is great. So it's a polynomial function of time. And now I claim, so by the time you're done, you get a picture like this, don't you? Yes? A polynomial function of time, but a polynomial that is constant over a small time interval must be constant everywhere. So this sum, which is the sum of signed volumes, sums to something that's the total volume of the simplex, which is 1. And by the time you're done, it sums to 1 as well, although some of them are counted with negative areas. But then do you see that the ones that actually cover this simplex, there have to be an odd number, and one more with a +1 volume than with a -1 volume. Boom. Whoa, new idea. Very topological too. actually used this to give a new proof, that once I saw this, a new proof of another combinatorial fixed point theorem, which I won't talk about in this talk, but it's such a beautiful idea that it's worthy of calling out. Okay, I promised you a heartwarming proof. Oh, the signs are given by the determinant, and the determinant might be positive or negative based on the locations of the corners. Yeah. Yeah. And so when you see these two simplices, one simplex sort of turning over, at one point, that's where it goes negative, this one right here. So you see, this is going to be +1, -1, plus. Okay. Okay, heartwarming, that's heartwarming. All right. Okay, so here's a cool application. So a cool application of this is, one of the things that I have been interested in for a long time is game theory and using combinatorial, topological combinatorics to solve problems in an area known as fair division. So the classical question here is, how do you divide a cake fairly among several people? And you want to do this in a way that makes everybody happy, even though people have different preferences. We all have different ideas of what we think is valuable to us. I might like cherries, and Grace might actually like sprinkles, right? And that makes the problem interesting. Okay, so here is an approach due to Forrest Simmons in 1980. This is how I actually learned about Sperner's lemma, is through a professor of mine when I was an undergrad. And the idea here is to think about fair division problems, the space of solutions, whatever they are, as some kind of topological space. It has some kind of notion of when two divisions are close, or when two, whatever it is you're interested in, are close. And so the idea to find a solution is to discretize, which means triangulate. It means then labeling the preference of the vertices using preferences. That's where the label comes from. And then it involves proving a discrete version of the solution exists. So this is Simmons' approach to cake division. So here's a piece of cake. I'm just thinking about cake as being a linear cake. Okay. And now I have knives that cut the cake, let's say for 3 people. Here is a potential division I might offer to 3 people, right? And Grace might be actually very happy with this because it has a lot of sprinkles, even though it's not the largest piece, right? People have different preferences. Now, if you parameterize, if you think of every division as a set of widths, physical widths, not preferences, X, Y, Z, then every collection of widths parameterizes this into a space that's a triangle. Every point in it, in the space of cake divisions, is a triangle. This is the one where the blue piece has all the mass. This corner is where the green, yellow piece has all the mass. And the last one's where the red piece has all the mass. And then if you ask me to find this point, well, this one is actually sort of closer up to this corner because this is a bigger piece. You with me? Every point is a division of cake. And once you realize that, then here's one way to think about what, dividing the cake fairly so that no one has any envy. You assign owners to each of the corners, and I won't tell you yet how we do it, but let's assume that's Alice, Bob, and Carlos. Okay, so there are 3 people, and you say, okay, give owners to every corner, and then at every corner you ask whoever owns that vertex, you say, hey, Bob, which piece would you prefer if the cake were cut like this? I have no idea what Bob would say, but I do know that if all the players are hungry, then no matter who owns this corner, Alice, Bob, or Carlos, they're going to answer 2 because they want the piece they don't want empty pieces, right? Similarly, in this corner, whoever owns this vertex, no matter who they are, is going to answer, I want piece 1. And all along the bottom, piece 3 is empty. So they're only going to answer 1 or 2. So if you went through and asked everybody at every vertex which piece you prefer, you get Sperner labels, don't you? In a very natural way. Okay, nice. Y'all are smiling. That's good. I didn't hear the oohs and ahs, but you're smiling. That's awesome. Now, of course, Now we'll pay attention to how we assign ownership. We're going to assign owners to the corner so that every corner is an Alice, Bob, Carlos triangle. And you have to convince yourself that's possible with certain kinds of triangulations. But if you're careful, you can do something like this. And now a 1, 2, 3 triangle means that for 3 very nearby divisions, Alice chose piece 1, Carlos chose piece 2, and Bob chose piece 3. For 3 very nearby divisions. So that gives you an approximate solution. And and many people are happy with that. Like, up to a crumb, you're not going to care so much. But if you really want the existence part, you could do this for many different size triangulations, subdivide. It's a little more complicated because when you subdivide this small 1, 2, 3 triangle, it's not necessarily going to be Sperner. So, the whole space is compact, and if you can find then a subsequence that converges to a point, which is also nice to do in an analysis class because they're like, what, convergent subsequence of triangles? Yes, you can do that too. Awesome. Okay, so that point is going to be the NV-free division you're seeking. Notice it may not be inside the triangle at any stage that you found, the 1, 2, 3 triangle. Okay, so the cake cutting theorem basically says this: if you have hungry players and if preferences are unchanged by limits, call that closed preferences, then there exists an NV-free division. All right, and a version of this theorem has been known since at least the early 1900s using measure theory, but constructive arguments are hard to come by. It was only in 1995 or so that someone actually had a constructive way of finding doing the n-person NV-free, solving that problem. But what this offers is approximate NV-free, and it doesn't involve cutting the cake into lots of different pieces. You only need the minimal number of cuts. And so, when I learned about this, I was in grad school, and my PhD was in probability theory, a completely different area. I was looking for distractions, and one of my friends came to me and said they'd moved into a house, and the rooms had different sizes, and they had a trouble deciding how much they should price the rooms at. Right? So my friend asked, is there always a way to divide the rent in such a way that each person would be induced to take a different room, right? Because a small room, somebody might want a small room if it's quiet. So you have different preferences, but nobody in their right mind would would pass up a free room. Well, maybe you have to think about that. So it turns out that if you think about the labeling conditions here, where you're seeking the 0 rent, not the highest rent, then you get a dual Sperner labeling, which is not hard to show and has been known to produce a similar result, a 1, 2, 3 triangle. And so here's a theorem that uses these conditions. Good house, every division you can at least say there's 1 room you want, which is not going to be true for like a big house that's $1 million a month. Like, division where everybody's paying $250,000 a month is none of those are going to be acceptable. Miserly tenants, no one pass up a free room, and closed preferences. Then there's an NV-free rent division. Now, you could solve this with linear programming if preferences were linear. And so the key thing here is that they don't have to be linear to show that there exists division. Okay, so that's Sperner's lemma. Now, when I tell you about polytopal Sperner lemma, which when this project first started, it was just a curiosity, and I was reading some papers on Sperner's lemma. I came across this one by Matanasov, who asked, is there a polytopal version? And I thought, oh, okay. And of course, what was known at the time is it was true for polygons. So if you have a 6-gon, then so what's a Sperner labeling? Sperner labeling means you label every corner differently, and along the 1, 6 edge, you only allow 1s or 6s. You with me? and along it, etc. 2, 3 edge, 2, 3. Inside could be anything. And so now the question is, well, you can't have a triangle with all 6 labels, but you can have a triangle with different labels. Okay, so that's maybe the next best thing. We call that a full cell. Sometimes people call it a completely labeled cell, but this is a full cell here. And so the question is, can you guarantee a certain number of full cells? And so what people knew for polygons is that you could always get n-2. And so the conjecture was that there must be n-d of them for an n-vertex d-dimensional polytope. And so a senior thesis project by Elisha Peterson, who's an undergrad, proved it for simplicial polytopes, which are polytopes with simplicial faces. And then with Jesus de la Vera, we generalized that to prove the whole thing. And so I'm just going to give you the idea of the proof, 2 different proofs. So we provide 2 different proofs in this paper. The first one is a path following proof. And so how does that path following proof go? Well, you have to decide what the doors are. And you have to decide what the rule is from walking from room to room, because, you know, like this is not as complex as it can get in higher dimensions, but, you know, it's not clear. I mean, this network, if you follow doors from the edge, is going to produce something that is not just a bunch of paths. Okay, it's like a spider-like graph. Okay, so you have to be very careful what you call a door, and so it turned out that's easier to do when you have simplicial faces than when it's not, and so it became complicated. But that's the basic idea. Okay, here's the topological proof, which many of you will appreciate, being topological if you love topology. The topological proof basically notes that whenever you have a triangulation of a labeled triangulation, this naturally induces a piecewise linear map where you send everything labeled 3 to the corner of 3. Okay, kind of like that animation earlier, except we're not going to do this slowly. We're just going to boom, map it. Now, topologically speaking, because of the Sperner labeling, you can argue that the boundary winds around once, and so the interior must get covered. So if you think of this as saran wrap, and me following the rules that say, oh, put the corner of this saran wrap 4 and 4, and just do that, basically you get saran wrap covering your dish at the end, okay? Because it winds around once. That's the topological part. Yes? All right, so now, how are we going to find cells that have different labels, like 1, 2, 5, or 2, 3, 5, or 3, 5, 4? So the key insight here is to try to do something like, okay, look at the inverse images of where the saran wrap where the saran wrap is coming from. The key insight here is we found a set of n-d places where you can put rocks down, such that every simplex of the triangle of the polytope that you only uses the corners of the polytope contains at most 1 pebble. And the idea is find as many of these pebbles as you can. Their inverse images must correspond to a fully labeled cell, because if this one lives in 1, 4, 5, or 3, 4, 5, or there's lots of other possibilities, it has to be covered at least once. Where did it come from? Well, it either came from a 1, 4, 5, or a 3, 4, 5, or a 2, 4, 5. Right? So if you find n-d of them, then you're golden. And so that's what we did in this proof. All right, so say again. If you follow the volume argument here, at the end, what you're going to get is a thing covered, but then you still have to decide. So some of those volumes are not going to be the full. Not going to, if 1 is the full thing, it's not going to be 1. And so what's going to happen is it'll be covered by pieces of saran wrap back and forth that sum to 1, but you'll need something like a a set of pebbles here to argue that it's going to be, I think you're going to need something like this instruction to say how many simplices you need. Now, one thing your question gets at is also the idea that the location of these pebbles actually determines could determine, it's a lower bound for a minimal triangulation of a polytope. And then the other thing that's curious here is it's not a parity result because this whole thing does not get covered. All right, so I'm going to tell you this is going to be very quick. So I'm just giving you a sense of like the potential surprising application. So one application was thinking about, well, what other fair division problems could this solve? And so if you take, for instance, two cakes where people's preferences over the two cakes are linked, then you might ask, is an envy-free division possible if somebody chooses one piece like B and from the first cake and A from the second? And you need them to be people to choose disjoint piece selections. It turns out that, if you think about the set of divisions of two cakes into two pieces, that the space of divisions is a square. And if you label the corners, label the vertices by which piece people are naturally led to choose, you get a polytopal Sperner labeling on the sides of the square. And so in higher dimensions, it would be a product of simplices, and you can do something similar. And so we have results. You don't need to read this closely, but just to appreciate, like the results are basically involve looking at polytopes in high dimension, applying polytopal Sperner, and being able to say what is and isn't possible for making people happy with multiple pieces. Here's a second application, minimal triangulations. So it's completely separate from this. I was working on a problem with a student looking at minimal triangulations of cubes. So here's a minimal triangulation of a three-dimensional cube. And when I say triangulation, I'm allowing interior vertices. This is what we call a vertex triangulation, where you don't allow interior vertices. We are interested in knowing what's a minimal triangulation in the top sense of a cube. And it wasn't known when we started thinking about this question whether in 4 dimensions that was 15 or 16 if you triangulate a 4 cube. So what was known is that for vertex triangulations, the answer had to be 16. So Mara in 76 gave a triangulation. This is the graph, what it looks like of the triangulation, vertex triangulation. But nobody knew if it could be smaller. So there's a paper that uses hyperbolic geometry by embedding the cube in hyperbolic space by Smith that showed 15 was known. And if you ask me later, I'll tell you about that proof. It's interesting. But we didn't know it was 15 or 16. And so our insight here was to look at the question for covers, which are allowing simplices to overlap, kind of like that picture, the animation. And if you just take a triangulation of a polytope and you assign it any polytopal Sperner, then you can see that that piecewise linear map turns into a cover. A triangulation with interior vertices turns into a cover that only uses vertex triangulations. And so from there, that was the key insight that allowed us to raise the lower bound to 16. So there's some questions here that we don't know. This actually works in high dimensions. And so now our lower bound raised the best known lower 5 cube triangulation to 60. A construction shows at 67. And we don't know the answer to that question. So there's a question you might be interested in. And then is there a minimal triangulation of cube that isn't a vertex triangulation for some high dimension? That's not. Multi-labeled Sperner. Oh yeah, so in 2019, I started thinking about this question with Frédéric Meunier, who's a French mathematician at the NPC, which was if you have a Sperner labeling, if multiple Sperner labelings at once, so the red labels by themselves are Sperner, and so are the the blue labels. The question was, can you think about the interactions between these labelings, and what could that do for you? And so it turns out that for a triangle with 2 Sperner labeling, because 2 plus 2 is 4, you can find a triangle with at least using a certain number, specified number of labels in one labeling and in another. Or you could break up partition 4 into numbers such that this one answers the question, how many labels are used by a specified number of labelings? And so we have a generalization. We knew that this thing was probably true because someone had a topological argument. And the question was, is there a combinatorial argument? And it turned out Polytopal Sperner answers this question. And so how does it do so? We basically looked at this simplicial map that's defined by the two labelings on a product of simplices. And certain points on one side, which I can tell you later if you ask me, correspond, their inverse images correspond to the kinds of special triangles that we were looking for in the other side. So, and so this turned out to be a little bit of a surprise for us because we weren't even thinking Polytopal Sperner. And so it leads to some new Fair division results. So, so it turns out that it was known through another route that if you have a cake, you only have n-1 players, you can divide the cake into n parts so that no matter who arrives later, no matter what their preferences are, there'll still be an envy-free assignment. That was known. We could prove it using this theorem. But the one we're proud of is the dual turns out to be true. You can divide a cake into n-1 parts so that no matter who is kicked off the island tonight, what remains can still be divided in an envy-free way. No, you can't. That's right. Because that assignment may change depending on who gets voted off. All right, I'm finished with this. So it always struck me that, like, you know, Hex is related to Brouwer. There must be. This is a polytope. This is a square. Come on, for crying out loud. There must be a polytopal Sperner proof. So I'm going to show you the idea of a polytopal Sperner proof, which I have 2 minutes to do. So basically, it goes like this. Here's a Hex board, which I'm going to assume doesn't end in a draw. I'm going to dualize it. So I'm just going to look at this graph. And I'll label, you know, everything comes now labeled by X or O because of the draw configuration. But I'm going to change the X's to either X1 or X2, depending on whether there's a chain of X's that gets me to the X1 side. And if it doesn't, I'll label it X2, even if it doesn't connect to the X2 side. Similarly for O, we're going to change them to O1 if there's a path to the O1 side. Now, what I want you to notice is by doing this, you can never have an O1 and an O2 being next to each other. Because this being labeled O1 means there's a path to the O1 side. This being labeled O2 means there's not a path, but there clearly is a path of O's. But now, if you're careful about what you're doing, you could think about what the labeling conditions are on the boundary. It's not Polytopal Sperner. But if you add vertices in the corner, it turns out it's Polytopal Sperner. It's square Sperner at that point. And so that means there's a simplex with 3 different labels, and 2 of them must be the same letter, both O's or both X's, which is a contradiction. End of talk. Thank you very much. You want to see Sperner in action. A reporter wrote me after seeing an applet that my student coded up with the Sperner algorithm in action. He said, I just used your app. This was way back in the days when apps existed, to solve my housemate problem. And he said, we'd like to code it up in a New York Times. And so I gave him the code, and I didn't hear from him for a year. And then out of the blue, he said, it's up now. So you can try out. This is a version of the Sperner.
So it's kind of the building block.
With the extra vertices? Yeah, so I guess what seems a little counterintuitive when one starts thinking about it is, okay, so the claim is you might, like, if I put in an extra vertex, I might have a smaller triangulation. And what's challenging about that is that when you put in an extra vertex, that seems to make it only possible to have many simplices because of that interior vertex has got to be a corner for many many simplices. So that's the intuition for why maybe you can't do better. Or maybe in a high dimension, someone, there'll be a surprising example where you can do better. I think the route back to that, to trying to answer that question might involve thinking about covers of polytopes and coming up with a nice cover that corresponds to the triangulation of a non-vertex triangulation. So I don't know if that answered your question, but those are the intuitions that I have around that. Yes. Good question. We were looking at the analog of the piecewise linear map in Sperner's lemma, and realizing that the inverse image of a simplex is not the whole simplex. Here, the inverse image of simplex can't be the whole thing. And so the question was, well, what can you say? And that led us to the idea of the pebbles. And that pebble argument actually turned out to be boiled down to some linear algebra, but it wasn't at least easy linear algebra for us initially. You need to be smart. Oh yeah. So there's a nice construction, and then it's what's harder is to show that construction has the property you want. But I'll show you what the construction looks like, if you want to know. This is actually really, really cool. I didn't choose to talk about, but in the polytopal case here, oops, this construction will work, the one that's in the picture, for a polygon. So if you take a facet and you cone to each of the other vertices, and then you put a dot in the corners, that will always work for a polytope. Actually, you can show that has the property that no simplex contains more of one of those dots. The problem is you can't show n minus d very easily, and it's not necessarily true for polytopes where the simplices, the facets aren't all simplicial, because you have too few of them. To get n minus d, so what was surprising was to get the extra ones, if this facet is not simplicial, you look at it and do the same crown construction in one lower dimension. And so that was like a moment where we're like, whoa, actually that gives the right number and it works. But then doing the linear algebra to show that it works was a little technical. Yeah. N minus d, yeah.
This line of work in science on these complexity classes that are associated with the top file. In that line of work, you have sense in Brouwer, Sperner, even the player Nash, are all equivalent to each other.
Yes.
I'm wondering, if you place this in that complexity zoo, does it also somehow still end up connected, or is there a form of complexity great sense which is a more higher complexity?
Yeah, I don't know. I mean, I haven't followed that closely. Every once in a while I get a paper to referee, and it's throwing around terms like PPAD, complete, and things like that. And I have not followed that. But some interesting complexity questions here. So for instance, what I was interested in was using this to actually solve fair division problems. And you can ask, like, oh, how good is this algorithm? It does seem, it might be interesting for someone to do this work, that in most cases that you care about, this algorithm actually finds a simplex relatively quickly. But the worst case scenario, I don't think can be very bad, but someone needs to prove it. I don't think it is as bad as searching it won't search the whole simplex, but maybe someone can do the work to figure out what that complexity is. And it's probably related to these things you're talking about. All right, thank you very much.